So, first of all, before I start today's webinar, I'd like to thank everybody who's attending today and listening into this event. And I'd also like to thank very much my colleagues in PT Multibangun Rekatama Patria who do such a good job in organizing these events. And I think if you've watched previous webinars, you'll see a new look to these webinars now, which is very nice. As usual, I have quite a lot of material to get through, so I think I need to make a start. And you can see the title today is about the performance of reinforced soil structures under extreme loading conditions. So just a few words about this. It is the 12th in a series of webinars that have been organized by PT Multibangun on the topic of geotechnical engineering. And this is a special title today, which you're by now well aware of. In fact, the extreme conditions that I want to look at principally involve tall structures, which obviously create high stresses. Then we have seismic loading, which can be very extreme, and also, of course, water pressure, especially when the water pressures are quite high. In fact, this will be the last, this 12th webinar will be the last of this style. And when we present our next webinar, which will be in April, there'll be a different approach, a slight change in the format of the material we present to you. But please look out for a notice about this coming up next month. Here is the full list of all these webinars that have been conducted. Of course, they were mostly last year, and we just have this 12th one to this year in February. So some images, tall structures. I said we'd talk about the effects of tall structures because they create such high stresses. The effect of earthquakes, which unfortunately can cause failures like this, and the effect of extreme water pressure and water conditions. That's the aim today. And what I would like to do is to look, in fact, at a variety of situations. We'll look at 3 tall structures. In 2 cases, there'll be earthquake loading, and in 3 cases, there'll be water pressure involved. And of course, there will be some combinations of the 2. And really, my main aim in doing this today is to look at this question. Could routine design and stability analysis have predicted what was later observed? And this is very important, really, because we rely on these techniques in our designs, especially in routine design, but we would like to have some idea if it would predict some of these sorts of conditions and events which took place. As usual, I have these little blue boxes which will come up from time to time with some special or additional information. And this is aimed at civil engineers who are involved in reinforced soil structures, and hopefully might be of interest also to more experienced geotechnical engineers and geosynthetics specialists. Here are a few abbreviations which you will see from time to time. I don't need to read through them. You can see them written down there, but this saves a lot of space and time later on in some of the slides. So we will set off. So I'm going to look at 5 cases, cases 1, 2, 3, 4, and 5. And this first one is to do with water pressure. And it was a wall built some time ago in Korea, and there is a published paper about it by Professor Chung-Sik Yu, and you can see the details there of the publication. Of course, Professor Yu is also the president of IGS, and he talked to us last year in an Indonesian chapter event of IGS on a similar topic, but not this particular wall. So a few details. This was a chemical plant in Korea, a modular block wall. You can see the range of the heights there. And what was rather important, it was supporting both an access road and utilities. And it was built in 1994-95. This is the details of the design parameters. We'll come back to some of this, so I'm certainly not going to read through that. You can see it for yourself. But perhaps the third one, rather important, is that in the original design, no allowance was made for any water pressure in the fill. And then what about the problem? Well, in August 2000, which was 6 years after completion, the owner noticed that there were lateral movements going on in the wall. And I think, as usual, this was occurring after a period of very heavy rainfall. So the client was very sensible and organized some monitoring to look at the deformations which were taking place. So here's a typical diagram of these deformations that were measured. You can see there against the section of the wall, you've got a diagram where you have lateral movement going outwards up the wall. So the diagram matches the cross section on the right. So there is a first reading. It was on the 7th of August that year. And then a little bit later, it had moved further and so on. So you can see there is clearly a concern that a structure which has been in position for quite some time is moving. And there was a second set of readings like this at a different section along the same wall. So this clearly warranted some investigation. This diagram is the horizontal movement versus time. So it had gone up to about 40 millimeters, if you recall, at the top. And in terms of a strain or an increase in strain in the reinforcement, those blue lines indicate that, in fact, the maximum increase in strain over that time period, about 0.6%, which is actually quite a lot for reinforcement which has been in position for a long time. So the concern about this was justified, and so was the investigation that took place. We've already noted that the deformation started after 6 years, and it's also fairly clear that the main deformation is taking place near the top of the wall, where the reinforcement layout is becoming much less. You can see the top few layers of geogrid, only they're all 1 meter apart. And it occurred after some particularly heavy rainfall. In fact, 500 millimeters fell over a 2-month period. Also, as part of the investigation, they carried out some additional sampling of the fill and testing, and they found typical results that you can see there. So based on this is a shear box test result, but based on this, they decided to back analyze using a phi value of 35 degrees for the fill, although the original design had been carried out actually for a 30 degrees, which you would think would be safer. So what I'm going to do then is to carry out some investigations using a design method based on 2-part wedge. And it's also a method set up following the principles of AASHTO LRFD. And in the results we see, the results are given in terms of what's called CDR, or capacity demand ratio. And of course, we want to see values that are 1 or greater, but you'll see in the internal calculations, if particular wedges have a CDR less than, a post-construction strain calculation to look at serviceability, also based on the same 2-part wedge approach. So here's an image from a computer program which carries out these calculations for you. I think it's fairly clear what's going on there. You have the section in the middle at the top. And in this particular input, we're inputting the properties of the fills, and you can see there a phi of 30 degrees. So I put phi of 30 there in large characters, so that reminds us what's going on. Now, when we look at internal stability analysis, you'll see that it doesn't look very good, a lot of red wedges. And then also, when I look at the prediction of post-construction strain, it's also rather high. We normally are aiming for a value of 1% or less, which is a recommendation from BS 8006. But here you can see it's quite a lot more than that. So you'd have to say, based on this analysis, that the initial design doesn't seem to be satisfactory. I thought it was also interesting to look at this using a stability analysis, where we have a special non-circular search routine. So there is the same cross-section. We're still using a phi of 30 degrees. And in this particular technique, we set up a family or a set of random non-circular surfaces, and then we run an algorithm which very quickly looks for the critical one. And currently we have a safety factor there, you can see it there, of just over 1. And as we run the analysis and the technique finds the critical surface, in fact, we find there we have a factor of safety slightly over 1. So you can see that this was a marginally safe structure based on the original assumptions. And also it seems that it is the upper part of the structure which is likely to be most critical. That's where the critical surfaces were. But what we'll do now is to switch over to a 535 degrees, which was used in the back analysis, but also look at the effects of water pressure by defining an RU value, which is one way to do that, and see what happens. So there is the structure again, and we're now going to switch over to a 535 degrees. And when we analyze this, in fact, we have no internal red wedges. Everything is looking good. And when we look at the post-construction strain calculation, we find it is slightly over 1%. You can see there from the diagram on the lower right. So it's not too bad. So with the higher phi value, the original design is just satisfactory. But then the issue comes if we add some water pressure. Now this is it. This is inputting water pressure. I'm going to do it using an RU value of 0.1. You can see there inside the red shape. So I'll just remind us that we're now looking at an RU of 0.1, and we start to get quite a few red wedges, which show, of course, an unsatisfactory performance. If I increase RU to 0.2, it becomes even worse. So clearly not satisfactory. And when I look at the post-construction strain prediction, we're back to that rather high value, somewhere over 1.5% for most of the layers of geogrid. So we can see that once you add water pressure to the original or to the design with the higher phi value, we also see an unsatisfactory performance. We can do the same thing in our stability analysis. So I'm going to put in an RU of 0.2 into the stability calculations. And when I do that, we find we get a safety factor slightly below 1. It's about 0.8, like that. There it is. And if I look at an RU, say 0.1 instead, a not so severe case, we still have a rather low safety factor, just around about 1. So a few concluding remarks on this investigation is that based on the initial parameters and conditions, the design was not satisfactory, even if it was dry. But when we take into account the higher soil strength, the design looks okay until we add some effective water pressure, which I did using RU, but of course you can do that in more sophisticated ways. So I think the performance that we see in this structure is really not surprising based on the analysis that we're looking at here. So that was case 1. Now I want to move to case number 2. It's also to do with water pressure, but it's also there's a high fill involved in this particular situation. So there is a structure built in the Middle East, and the wall is 19 meters high. You can see down there at the bottom of the photograph, and it supports a very large 63-meter high top slope. And in this particular picture, it's nearing completion. So here's a cross section of the structure. So the reinforced soil wall, although it's quite big at 19 meters high, it's actually quite small compared to the overall fill. But also of interest in this particular case was that we have a culvert that runs through the base of the fill. You can see it marked in the bottom of the diagram there. There was, early in construction, there was an issue noticed that there was some outward deformation of the reinforced soil wall. So they installed some instrumentation to measure the outward movement, which was done by simple survey targets. So there is the front of the wall. This is partway through construction. Wall is completed, but the backfill isn't. And if you look very closely, you'll see some cracks in the concrete of a parapet that's built around the culvert exit point. And this was a concern, so this was the reason for setting up some instrumentation. So there's a view of the front of the wall, and all of those red circles, sorry, all of the round circles indicate locations of measurement points to measure the outward movement of the wall. So if we go back to our cross section to remind us what it looks like, and then what I'm going to do to make it easier to see what's going on, I'm going to kind of squeeze it over to the left in an exaggerated scale, so I can plot a diagram in the remaining part of the slide to show you the deformations that took place. So here is the graph. The graph is in the horizontal axis is time in days, and you can see there's about 4 years of data there. And we have the height is the axis on the right-hand side. And you can see there in that yellow line is showing how the structure was built up. It took quite a long time for the total construction, as you can imagine, for such a huge fill. And if I then superimpose the displacements, sorry, just to remind you, that's where the fill was at when the monitoring was started. It was already at that level. So if we look at the outward movements where I've put that red arrow, then it looks like this. And you now read this on the left-hand axis, the displacement in millimeters, and you can see as they built up the fill, the wall was moved forwards by something like around about 20 to 30 millimeters. And there is one long-term reading as well, taken 2 years later, but unfortunately the control was not completely reliable for that. But it shows that there was some further movement, but not very much. So there we see a record of this kind of the behavior of a wall like this, but that actually isn't the main point. What was really interesting when they set up the instrumentation was that the culverts were built in 10-meter sections with joints. And so the contractor decided to actually measure the expansion of the joints to give some indication of movements within the base of the fill, which is actually a very smart idea and a very inexpensive way of doing some monitoring. So we'll have a close-up. There are a couple of the joints inside the culvert, and you can see how they have actually both opened up. That's why you see the black is the gap between the culvert sections, which is developing, and they put measurement points either side, and they take measurements. And of course, these measurements are very accurate and resolved down to a small part of a millimeter. So again, here is another graph of the time in the horizontal axis. This orange line is the height of the fill, and then on the left-hand axis is the expansion of the culvert joints, and that's what's in the colored results. So what you can see is there that over that particular time period, you can see from about 250 days to 330 or so, you can see that the culvert joints are opening up slightly by a few millimeters. But then what's very interesting is that suddenly at around about that point, all results suddenly increase by quite a lot compared to the original trend. And then beyond that point, they kind of become fairly static. There isn't very much movement until a bit further on, they carry on increasing again. So of course, whenever you see a sudden change in a performance like this, there's a question mark in your mind, and why did that take place? And just to also point out that in fact, although it looks quite dramatic, a 5 millimeter expansion in a 10-meter long culvert is a strain of only 0.05%. So it is actually a very small strain. But in carrying out investigation, it was discovered that there was a major rainfall event at that point in time during the construction. And as you can imagine, rain often gives us a slight deterioration of behavior when we look at these structures. but it's interesting to look at it and think of how it could be happening. So if we now go back to our cross section, then we need to be aware that in this particular structure, the general fill was an open graded rock fill because it was coming out of mountains. It was large rock sizes with big large pore spaces between them. So an extremely high permeability, but the specification of the reinforced soil block itself was also a granular fill, but it was a well-graded granular fill. So it was of relatively low permeability. And this is a detail which is really important to have a think about. So at the time of that sudden increase in movement, the fill had reached the level given by the red dotted line. So if you can imagine, the fill's reached that point. We have a very open graded fill over most of this huge area, and it rains very heavily. And the rain therefore gets into the open graded rock fill and puts a large amount of water pressure on the back of the reinforced soil structure. That would be the interpretation and the reason for the sudden increase in deformation, or the rate of deformation in the culvert joints. So it's an intriguing behavior, and it's not quite the end of the story. So there is the structure again. And as I said, the issue here was that we had a relatively low permeability reinforced soil structure with a very high permeability backfill. So that means the reinforced soil structure acts like a dam in a way. But there is actually another incident that took place much earlier during construction, which is quite fascinating. And the next slide will show you a video. It's quite loud, so be ready for it. So let's have a look and see what happened. This is sometime earlier on during the construction. I think you'll agree, a quite extraordinary video. And in fact, following that experience, there was a very nice statement which came from it was the contractor's project manager. And he made this very nice statement. I won't read the whole thing out, but essentially the really excellent behavior helped him to sleep at night, because you could see how well these structures could perform under such an extreme loading situation. But what was actually going on there? We saw that water pouring off the top over on the right-hand side. So, well, I mean, I wasn't there at the time. I can't be absolutely sure of this, but my assumption is like this. So let's go back to the full cross-section of this particular structure. At the time of that particular rainfall event, there was no monitoring yet. They hadn't had the problem with the culvert exit, so they weren't monitoring anything at this stage. But at this stage, the fill height had reached something like that. In that picture just now, the wall was about 7 meters high. It wasn't completed. So you have that same situation of the very porous rock fill, the light yellow color, and the low permeability fill of the reinforced soil mass. So it rains, that's meant to indicate heavy rain, and it would be my assumption that this fill was so porous it could fill up with water, because the water's coming down the valley sides, it's coming from all over the place, and it's concentrating in the bottom of the valley, and essentially it fills it up. That's the only way I can find an explanation as to how the water, with that little blue arrow there, was running off the top, as we saw just now. So this is certainly an extreme event. So it's interesting just to spend a minute or two looking at the stability of that part of the retaining wall, because it stood up beautifully. There was no problem with it, despite the fact it may have been supporting a full height of water pressure behind the backfill, or behind the reinforced fill. So let's just have a look at a couple of calculations to see if that makes sense. So again, I put this case into a reinforced soil retaining wall design program. It's the same two-part wedge one, but I'm not interested in internal stability. That's no problem. I'm interested really in sliding. So if we look at this particular analysis at the moment, the sliding CDR is over 8. In other words, it's enormously high. Not surprising, you have a very wide reinforced soil block, very good conditions. And at the moment, we're assuming all the water pressures are 0. And I can also look in the detailed calculations for this particular case. When I look at the forces behind the reinforced soil block, you can see there inside the red shape, we have just over 100 kilonewtons per meter coming from the backfill. So remember that number, just over 100. Okay, so now let's try to imitate what we saw. So what I'm going to do now in the input of the water pressure, I'm going to put a 0 water level within the reinforced fill and a full almost 7-meter height within the backfill. So if I do that, I now get a section that looks like this. And if you look very closely, you can see up there the water level line at the top of the backfill, but you can see within the fill it's at the bottom. Okay, so if I now look at my calculation results, the CDR is half. It's now around about 4. It used to be 8. So the effect of that water pressure has halved the resistance to sliding. It's still very high, of course. And if I look at the actual forces, we now have this huge force from the water pressure. In fact, the total force now is almost 300 kilonewtons per meter. It used to be just over 100. So the effect of this water has been to cause an enormous increase in the force on the back of the reinforced fill. If you want to look at an even more extreme condition and assume there was some water pressure buildup within the reinforced fill, which probably didn't happen, but maybe it was possible, then of course we get a slightly lower CDR value on sliding there. It's now just over 3. And of course in here, the forces from in the backfill are the same, but we now have an uplift force coming from that water pressure, which is the reason for the drop, further drop in the sliding resistance. So the structure performed perfectly okay, of course, but it is interesting that analysis does show us quite nicely, and that could well explain from that information we saw with the culvert expansion, or the joints, the culvert joints expanding from that monitoring that came later on, a very good explanation of why we had a sudden increase in the rate of the outward deformation. Anyhow, all was well. The rock fill could be easily drained. But there's a very good lesson that comes out of this, and that's to take extra special care when you're designing structures with fills of varying permeability. Even if they're all granular fills, then look at the relative permeabilities of the fills to make sure you're not creating a situation where you can dam up the water. Case 3. Now, case 3 is this is a case I've shown before in a previous MRP webinar, which is it's actually a shaking table test. So we're now interested in looking at a wall under strong seismic shaking. Because I presented this before, I will be reasonably quick about the outline. But what we're looking at here is a shaking table, and it's a full scale wall that's going to be built on this table. There are some published papers about this. It's now from a few years ago. And there is the container which holds the retaining wall, and there is the view of it. So the wall is 6.1 meters high. It's a full scale wall. It's a sand backfill, modular block facing, and the total weight of the model is over 800 tons. And the design of it was actually carried out for a horizontal acceleration of 0.7 G. Now, in reality, when they tested this wall, they actually shook at a total of, with 41 different excitations of the shaking table, which included 3 real earthquake records. And the strongest that was reached was 0.55 G, which was actually a model version of the Kobe earthquake. And the coming video, which again I've shown before, but it's always worth having a look at, shows the actual behavior of this wall during one of these shaking events. So there's lots to look at. You'll see a view on top. You'll see some movements of the wall, and you'll see the accelerations that were being created. So again, it's a slightly noisy video. So off we go. Oh, sorry. Before I get there, here is the cross section of the wall. We'll come back to that in a second. Lower left is the acceleration record, and up top right is the backwards and forwards movement of the wall. And the video pictures are fairly obvious what you're looking at. And if you can just look at the scale, the actual accelerations went well over 1G just for brief instance. But it really is the most incredible record of the behavior of a structure like this during a strong earthquake. Just to show you in a little bit more detail, the inward and outward movement. If there is the cross section of the wall and the graph is going to show you the backwards and forwards deformation, then from the initial position, the furthest outward movement looked like that, and the furthest inward movement looked like that. And after all the shaking had finished, it ended up back almost where it started. So it really was the most excellent performance of such a structure. After the completion of all the shaking, they noticed some cracks in the backfill, and the whole system of deformation looked very much like the formation of a two-part wedge system or mechanism. And so that's what I want to do. I want to examine this behavior using a two-part wedge method. So just to remind you, the wall was designed for 0.7 G, but the maximum acceleration achieved was actually 0.55. So let's have a look at that. So we're back in the program now, which uses a two-part wedge method. The geometry of the wall has been put in there, and you can see there on this there we are. So we're now looking at the acceleration of 0.55 G, and the phi constant volume for the fill had been established or measured at 38 degrees. So you can see with these conditions, we begin to see a few pink or red wedges appearing. And the critical plane would continue up through the backfill at about 45 degrees if you had the full mechanism. And if I then look at the details of these wedges, I see that I have some where the CDR has dropped just below 1, about 0.8. So we can see under these conditions, the CDR slightly below what you'd want, but this is using phi CV. Phi peak was 42 degrees. And if I switch over to phi peak and look at the similar results, in fact, the lowest value of CDR was over 1.5. So this probably explains quite nicely why the structure, although it did start to show some signs of cracking, but it performed very nicely under this level of shaking. And here it is being, if you like, confirmed by a simple static analysis, which is really quite nice, because this is a very common technique for carrying out designs of this form of structure. If I now look at 0.7 G, which was the original design acceleration, even for phi peak of 42, I start to see one or two red wedges appearing. And if I go to 0.7 G at phi CV, then in fact the lowest values are going all the way down to 0.45. So would it have survived 0.7 G? Well, we don't know because it never reached it, but clearly it would have been pretty severe shaking situation. So that's just a summary. You can see there that if we look at the actual acceleration maximum value, which was PGA of 0.55 G, then the results are very good. And the critical wedge angles are very low, as you can see. That's phi critical, or sorry, the sigma critical that you can see there in the brackets. Sorry, theta critical. So this in my mind shows that these techniques can work very well in a situation for designing or predicting behavior of a retaining wall under strong seismic shaking. It's also perhaps interesting to have a look at the effect of a stability analysis using a special technique, and we'll look at only the PJ of 0.55 G. So there is the cross section, and we're going to use a special technique where we search for the critical case, as we did with the first wall, the Korean one. So there are a series of random surfaces, and then this algorithm runs until it finds the critical condition, which is a very low angle wedge like that, and the safety factor slightly below 1. And if I then switch to a phi CV of 38, then safety factor a little bit lower still. But again, it is showing, first of all, that the mechanism matches quite well with what was observed, and we're getting a result that would be satisfactory and as expected. Now, case number 4, in this particular one, I want to look at a case that I presented at a previous MRP webinar. But I think it's worth looking again because it fits into the topic today of being an extreme event, because it's a tall slope and it gets affected by seismic shaking. It took place during the Chichi earthquake, and there's a number of papers have been published about this particular slope. It was at the Chinan University in central Taiwan, and this particular paper there, one of the authors there, Professor Kuo-Sin Yang, he talked to us in an ENA IGS webinar last year as well. So another one of our speakers from last year who was also involved in investigating this particular case. And in that particular paper, there are 3 failures that took place within this structure. One during construction and another one during the earthquake, and that's the one we want to have a look at, and then another one associated with heavy rain. So we'll investigate the second case. So there is a pictures. I said I've shown these before, so I'm going to be fairly quick because I want to have some time to make sure we go over the case 5 quite carefully. So there it is. So this slope was pretty big. It was overall height was 80 meters, and the lower part of it was reinforced. Not the entire 80 meters wasn't reinforced. It was the lower part that was reinforced. And during the Chichi earthquake in 1999, which was quite a strong earthquake, some of you might actually remember it, others of you may have read about it, but it caused a lot of damage, including to earth structures. And this particular failure was of great interest to many people, and many people investigated it and analyzed it and so on. But I just want to repeat this case today because it is so relevant. There was the slope as it was built before the failure. It's very important to realize that the lower slope, the one at the slightly lower angle where you can see the drain running up on the right and left hand sides, that's not reinforced. So that's an unreinforced slope. The reinforced part starts above that, where you see the slightly thicker grass. And that's the view looking the other way. In fact, you can see that there were some concerns about this lower unreinforced slope, and they actually put some ground anchors in there. You can see from the ground beams there that there was some strengthening done of that particular part of the foundation of the slope. And this is the cross section, and this cross section, the scales, horizontal and vertical, are the same. So inevitably, when you look at this cross section, first of all, you can see it's a very big structure. Its overall height is more than, was around 80 meters, but the reinforcement looks incredibly short, and indeed it certainly is. And it's of course therefore interesting to analyze this with 2 targets. First of all, in the static case, it was standing up. So would you expect that? And then would you expect to see the performance that later on happened during the earthquake? So we'll carry out analysis using the non-circular technique, which I've shown to you before, where we create a family of possible non-circular surfaces, each one made of 15 lines within certain bounds. And having done that, we then use this genetic algorithm to very quickly fine-tune the search and find the critical case. This is the static situation. And in the static case, this safety factor comes out at something very close to 1. And the fact that the structure was standing up confirms that this was okay, it was stable, even though maybe the safety factor wasn't as high as it might have been. But you can see how the non-circular search has worked very well. You get a steep failure plane behind the reinforced soil structure, and then it turns and makes its way quickly through the reinforcement at the base of the slope. It's what you normally see in that style of analysis. So there's a safety factor. Okay, so now let us remind ourselves what's going to happen with the earthquake. So there is the a view up the slope before the failure, and there's a similar view at the base of the slope after the failure. Now, one thing that is very clear from this is that the foundation failed. That lower slope where they had the ground beams and the anchors, that failed because the ground beams made their way across the road, were pushed across the road by the failing soil mass. So the form of the mechanism of failure is quite clear from that. There's a general view of it, and you get a good idea of the scale there because that's Dr. S.S. Lin standing in front of it there, who some of you may have heard of from Taiwan, having a careful look at the bottom of the failed soil mass. But you can see what's happened in that lower slope. Right, so if we go back to our cross section, this is still the static case, but I'm now going to add some earthquake loading, and many people were analyzing this with a horizontal ground acceleration of about 0.3 g, and vertical was set at 0. You can read that in the middle, I hope, there. So I'll just summarize that by one single arrow, 0.3 g horizontal only. And if we analyze this case with that same mechanism, we find that we get a failure that goes through the reinforced soil structure. And in fact, many of the analyses presented of this particular structure, they all tend to look something like that. But that was applying a purely horizontal acceleration, as I mentioned just now. And one thing that was very clear from the records from the Chichi earthquake was that the vertical accelerations were also high. So this means you could have a moment in time with a very high vertical acceleration and maybe a smaller horizontal acceleration. So I'm going to change things over a bit and look at a case like this, where we have 0.1 g horizontal and 0.3 g vertical up and down. And when I switch over like that and I run the same analysis, I find that I get a failure that is coming through the foundation. So what you're seeing there is really what happened. That was the place that it failed. That's where the ground beams were pushed off across the road. And if you look at if you can just read the numbers in the yellow down the bottom there, you'll see it says D after each one. D stands for down. So it is the downwards vertical acceleration which is giving the critical case. So what's happening here is that this large amount of extra downward inertia has obviously increased the forces for a very short length of time within the soil mass at the toe, and has created a failure, just like we see there. So that's what actually happened. Yet here's an image from one of the many publications about this particular case. This is not a calculation done by me, but many of the published analyses look like this, and they show the failure coming through the base of the the reinforced soil mass, which was not the case. It was through the slope underneath. So I want to move on to case 5 now. And this is to look at a high slope with possible water issues. Now, the slope is actually the Yeager Airport extension in West Virginia in the USA. And this was a very large 45-degree reinforced fill slope, up to 74 meters high. And it was built in 2005 to 6. And it was to extend a runway. It failed dramatically on the 12th of March, 2015. And at that time, for those people who keep an eye on these things, there was an awful lot of information and opinion being published on various websites. There were many photos and reports and videos becoming available. And the really good thing is now that we now have a very thorough forensic investigation that was carried out by a team of people led by Jim Collin and Ryan Berg. And some of you might remember that, again, at an Indonesian chapter of IGS webinar last year, Jim and Ryan talked to us and presented the information about their investigation into the Yeager slope failure. So for what actually happened, then the place to go is to the papers and the material published by Jim and Ryan, because I think for anybody involved in structures of this nature, such big structures in quite difficult conditions, then the lessons learned are really important. Today, I don't want to talk about this. I want to approach this in a rather different way. And in fact, the comments that come, which follow, are really my own personal observations based on information available before the failure took place. So going back to my original theme was, would you expect the behavior that you see based on the initial analysis of the situation? So that's what I want to spend a little bit of time looking at, because although this analysis has become superseded by the work carried out by Jim and Ryan, I think it's still got some interesting conclusions and features that come out of it. And I thought it was worth spending a few minutes looking at this as the last of the 5 cases today. The pictures are well known by now. So very quickly, there was the completed slope. The reinforced soil structure is the bit looking over on the right-hand side. And just a few bits of information here on the dimensions. You can see there, I don't need to read through it all, but it was a very high slope. The reinforcement was very long, and there was a downward slope below the toe. And you can see there the properties. Now, these values are all taken from publications available before the failure took place. In other words, they've been published before the event. And also the same with the geometry. So again, the geometry which I've used in this analysis was as published. But again, I'm interested to know that, could you anticipate what happened based on this information? There is a cross section. If you want to know what it really looked like, again, go to the publications from Jim Collin and Ryan Berg. But you can see it is a huge structure. You can see there from the meter values on the grid lines, the 74-meter height, and also the toe slope at the bottom. And so I want to analyze this and based on what we see at this stage of the project. A few construction pictures. There's the reinforcement being placed. The fill, you can see, get some idea what the fill. The fill was rated to be a good fill. There it is as it's going up during construction, nearing completion, and now the unfortunate event when it fails. You can see the failure there very clearly, running all the way down to the road below. There is the backscarp, and there's this rather famous picture showing all the reinforcement. So what was interesting about this failure is that the failure went right through certainly the upper part of the reinforced soil mass, which is quite an interesting observation. So just a few words about it. so at the time of failure, the slope was already 8 to 9 years old. So this is actually a delayed situation, a little bit like the first case, the Korean Wall. That one was a poor performance that took place 6 or so years after completion. So there's a kind of similarity there. And the case study is mentioned in the FHWA manual NHI 10025, which covers principally the design of reinforced soil slopes. And already mentioned the terrain below the slope falls away quite steeply. And there had apparently been an earlier history of instability, but really that information is all covered very well in the documents published by Jim and Ryan. And deformations had been noticed about 2 years before the failure took place. So to investigate this, I just used the method of slices to analyze the slope using a circular surface and with a target safety factor of 1.3, which would be as per the FHWA manual mentioned there. So back to the cross section, this particular technique has a very nice search technique for circular surfaces. So you can essentially define a huge zone of centers and radii and so forth. And then the program very quickly finds the critical circle for you. Now, if you can just read there inside that red circle there, it says the minimum 1.229. So that was after searching a huge number of possible circles and the safety factor 1.229. So that, assuming the target was 1.3, then that would be a little bit below the target. So this got me thinking as to, is there an explanation for that, if that is the case? And in the same FHWA manual, NHI 10025, there is this diagram which is giving you some advice on carrying out circular analysis for reinforced soil slopes. And one thing it mentions is that if you have continuous reinforcement, in other words, like geogrids or geotextiles, then you can allow it to rotate and become tangential to the failure surface. And what does that mean? Well, it's inside that red circle. So rather than assuming a horizontal reinforcement, you assume that because of the movement going on, you will allow it to rotate. And what does this do to your analysis? Well, the lever arm of that resistance changes from being the vertical distance from the center to being the full radius of the circle. So it becomes much bigger, or it can become much bigger depending on the location of the reinforcement. So what I thought would be a good idea would be to understand the implications of that, because I believe this technique is used by maybe in some software or some methods, but I think it's worth having a think about this to try and see what's going on if you allow this to take place in analysis. So to help visualize this, I've drawn a picture there of a steep slope with 3 layers of geogrid, the red lines, and I'm going to have a circle that looks like that. Sorry, it's a kind of faint line, but it's a light green color with the center there. And when you do that, you can calculate what I call a development length, which can feed into the mechanism. So if you're going to have the geogrid rotating, then the geogrid has to, if you like, slide out of the resistant backfill or the moving part of the soil mass, and it has to then make its way, or it has to be stretched along the developing failure surface. And we can calculate that particular length. And so I've shown them that this development length will become smaller as you go further down the slope, because the pull-out resistance is becoming much higher due to the higher stress or the increasing stress as you go further and further down through the structure. And in fact, you can make a rough calculation of that length. I call it the development length. And you can do it by comparing the pull-out resistance to the tensile strength of the reinforcement. So the development length would be given by that formula, and that formula includes Z, the distance down to the reinforcement. So this means I can then calculate a relationship between the depth to the reinforcement and the development length. And I'm going to do it for a particular set of values. You can see there quite a high strength reinforcement and some other properties you can see. And the development length for different values of Z. So I got a Z of 1 meter, in other words, a very shallow geogrid, all the way down to 75 meters, which would be a huge slope. And the development length changes from 1.6 meters at the top, so a very long length that can be dragged out of the resistant soil mass, all the way down to just 22 millimeters at the bottom. And this has an important implication. So what I'm going to do now is allow this surface to actually fail. So we'll rotate it. So we start to rotate it. And as we do this, you can see how I've allowed the geosynthetic reinforcement to become dragged along the failure surface, except for the lowest one, which I'm going to assume fails very quickly because it's got a very short development length. And we allow it to go a bit further, and then maybe the middle one fails. And then we carry on a bit further, and maybe the top one never fails. So the point about this diagram is that the reinforcement is rupturing by unzipping from the bottom upwards. So the lowest geogrid fails first, and then the other ones above it as the failure surface develops. So what is the length of the geosynthetic that may be, if you like, stretched along the failure surface? Well, you can approximately calculate that. If we assume that the strain at failure is about 10%, then this delta LDEV, as I call it, would be something like this. So at 1 meter depth, it would be over 300 millimeters that you could drag that piece of geosynthetic along the failure surface before it fails. But all the way down at 75 meters, it's only 4 millimeters. So that's why I said that that piece of geogrid would rupture almost immediately the deformation started. And of course, this whole concept raises another important question. What is the appropriate definition of soil strength to use if you're going to take into account rotation of the direction of the reinforcement? Do you use peak, constant volume, residual? I think that's a difficult question. Anyhow, is there any justification for what I've just said? Well, I'm looking at another failure here. This is a project in Indonesia. It's near Purwakarta, where there was a railway embankment that failed, and I managed to go and have a look at it. And if you can just about see there, you can see lots of little kind of black lines and black material sticking out of the fill. And that's the edge of the geosynthetic. It's actually a geotextile. And the failure surface is basically that yellow circle there, which is close to a circle. And if I pick out a couple of bits of the mass, they're still horizontal, but in the rotating part, of course, they're now tilting. And you can be quite sure that the deep down in the fill, they had all ruptured. This is very clear. But if I turn around in my point of view there, and I look at the other side of this failure, which is there, that's looking the other direction, and I look up at the top, you can just about see it there. But if I zoom in to that location right up at the top, what do I see? I see this geotextile has actually been pulled and kinked downwards, just like the blue line in my diagram over on the top right. So although my approach was very theoretical, this kind of behavior can actually be seen in a situation like this. So the whole point about this is, if you're going to take into account rotation of the geosynthetic reinforcement, it won't reach its peak strength at all points at the same time. It'll rupture down the bottom while it's still developing its resistance at the top, which is one reason why I think personally it's an extremely unwise thing to do in analysis like this. But let's go back to our analysis and let's permit this rotation to take place. So here is the same analysis. Obviously it's circular. This is only in circular analysis that this is going to happen. And if you can read it down towards the left there at the bottom, it says danger, rotational shear in use. And when I do the analysis, I find that my safety factor is now 1.34. Yeah, we can see it there. In fact, if you run the analysis a bit more, it drops down to about 1.33. But the important point is it's now over the target. So by allowing the rotation of the reinforcement to take place in the analysis, then we can get a target safety factor of 1.3. But if you take this into account and you get this, the previous safety factor was about 1.29, I think. No, it wasn't a big one. It was about 1.22, I think. So you can see you've lost about 30% of your margin against failure by taking into account this technique. But please be aware of the consequences. Now, there was water at the slope, at the base of the slope, and so it might be interesting to see if this would have much of an effect on the analysis. So I've taken the same arrangement there, and I've just put a water table, as you can see by the blue line, and I've analyzed that, still allowing for rotation. And if I do that, the safety factor drops a bit. It's around about just about 1.3 now, rather than 1.33. And what's interesting is if I now go back to not permitting rotation, it's quite interesting that the critical surface is very difficult to see it, but it's a very faint yellow line within the reinforced soil mass. It goes back to the original failure surface with a safety factor of 1.229. So that was quite interesting. Also, let's have a look at using this simple genetic algorithm with the non-circular analysis, which I've said is the best way to do this. So back to our arrangement, still with the water level, a water table in it. I run this search technique with non-circular surfaces like this, and you can quickly see how the critical surface is developing, and the safety factor in this case around about 1.2, dropping down to about 1.15 was the lowest. So and that's with the surface now restricted to the reinforced soil mass. So the non-circular technique does indicate a lower safety factor. Now this is using the Jambu simplified method, which by itself is normally slightly conservative, but I think the indications here are that the factor of safety of this slope was a little bit lower than the target. Also, rather interestingly, is that having the water level at that particular place, as I've drawn it, didn't have a very big effect. And in fact, that was one of the conclusions from the papers and the publications from Jim Collin and Ryan Buss as a structure, and it had some significance, but not very great, which turns out to be the same as we see here. So there it is. So I think this is bringing me to the end of this presentation today. I said, if you really want to understand all the real issues at Jaeger, and there were many, then please read the papers and the material authored by Jim Collin and Ryan Berg. So I just want to finish off with a few summarizing points here based on looking at these 5 cases of what I call extreme loading. And the way it worked out, of the 5 cases, 2 performed well and 3 either failed or performed badly. And I'm satisfied that in all cases, a routine analysis. What do I mean by routine? I really mean limiting equilibrium analyses. They could predict the observed behavior satisfactorily. So many of you might say, well, why wouldn't you be rushing in to use FEA? And most certainly, yes, by all means, that would be a really good idea. I'm not sure for the ultimate limit state, you'd see a lot of difference in the results. But the point is that in most of these structures, to set up a full FEA model would be very time consuming, especially to do it thoroughly and properly. Plus the fact that you'd be very short of data, probably. So the actual improvement may not be that dependable, but certainly FEA, yes. But we tend to use FEA when we have specific situations we want to understand better, when we want to know more about deformation. But for most routine design that I come across, we're using limiting equilibrium. So I am happy that those techniques really work well in all of those cases. Now, a few final comments. This is from experience of looking at many of these structures over the years, but of course, all aspects of a reinforced soil design are important, the soil parameters, et cetera, but in particular, when you're looking at these structures, if you have a toe slope, which we had in two or three of those cases, a toe slope or a top slope, or you have water, which you're normally going to have, these require special attention. In fact, in the last two cases, there was a toe slope, and in both cases, they were involved in the behavior that took place. So be particularly careful when you're building very heavy structures on top of existing slopes, because you already have a situation there which may lead to instability. For internal design of reinforced soil structures, my recommendation is to be using either a two-part wedge method or a non-circular method of slices analysis. And if you're using circular analysis and you find you're making use of rotation of the reinforcement, as I described just now, please be very careful about it and understand the implications of doing that. And then finally, a point to make here is that when you're investigating designs for seismic areas, then it's a very good idea to look at combinations of horizontal and vertical acceleration, different combinations, especially when you've got things like toe slopes, because you're never quite sure what's going to be the critical situation. So that would be my recommendation in that situation. So thank you very much for your attention. I believe I'll have a look to see if we got any questions, but there is just a summary of all of these webinars. As I said, in April, we'll have a new style of event, and we'll be circulating a notice sometime in March about that. So thank you all very much for your attention.